class. This is physics for Monday, August 31st. Today we're going to talk about significant figures, and we're also going to do a quick review on doing some calculations using some powers and rates. So let's start it off. Quick review of our significant figures. Part of why we're talking about significant figures is to get into both topics of accuracy and precision. So I want you to think a minute, what do you remember as the definition for accuracy, as well as what do you remember for the definition for precision? So I'll go ahead and get you started after you've had a moment to think. Accuracy, this is the closeness to the true value or the correctness of the measurement. In other words, how good were you at getting close to the exact value? Right? How good were you at getting close to the exact value? If something is 5.17 meters, how close were you to getting your measurement to being 5.17 meters? Precision, on the other hand, is a little bit different than accuracy. Precision is more of how certain you are of your measurement. So I can say it this way, maybe the accurate number was 5.17. We can say with the precision of our instrument, maybe our instrument can only measure to tenths of a meter. So we're going to say, oh, we think it's 5.1 meters, but it could be plus or minus a tenth of a meter because that's the accuracy, or the precision rather, of our instrument. So just to keep those two concepts clear, accuracy, how close are you to the actual correct number, the real number, and precision is how certain you are of your measurement. And that really depends on how precise your measuring tool is. So this goes into where we come up with the concept of significant figures. And they're telling us significant figures are involved when we measure something, and we're telling us we're using that number of significant figures to tell us how precise our measurement is. Not how accurate, but how precise our measurement is. So here I've got a couple pictures of some graduated cylinders, if you can remember that from way back in chemistry. And we look at our first one here, we see that our graduated cylinder, the first tick there is a 20, and there's another tick, and the second tick after that is 40. So it tells us that every tick mark is an additional 10 milliliters. So if we're going to figure out what our measurement here is, well, we see it's greater than 40. We say it's less than the 50 milliliter tick mark. So we know it's going to be 40 something. Now, is it halfway between the 40 and the 50, or halfway? No, it's a little bit closer to the 50. So I'm going to kind of draw an imaginary line here where that 45 would be, halfway between the 45 and the 50, 40 and the 50. And then now, do I think it's closer to that imaginary 45 line or closer to the 50 line? Well, I'm going to think it's closer to the imaginary 45 line, so I'm going to say that I would call this measurement 47 milliliters. 47 milliliters. Now, quick refresher, this tool can measure to tens of milliliters. We're going to estimate that last digit. In this case, it's the 7. We're going to estimate that last digit. Right? We can't just read it right off of the tool. We have to estimate where it is between those two tick marks. So 47 milliliters is our measurement. How many sig figs do we have here? Well, you got 2 of them there. 4 and a 7. That's 2 sig figs. Let's look at our next graduated cylinder. In this one, we see that 35 milliliters is this big tick mark. And we go 1, 2, 3, 4, 5 tick marks before we get to the next one, the next big one, which is 40. So we got 5 tick marks between 35 and 40. So each tick mark means a milliliter. Now, if you look at this, this means that this particular tool can measure accurate to a milliliter. I want you to pay attention to this one over here. This one only could measure the accuracy of the precision rather, of 10 millimeters. This one can measure to a precision of 1 milliliter. But we always estimate that one further digit, right? So this is 35, 36. So it's between 36 and 37. Is it halfway between them? Yeah, it looks pretty doggone close to halfway between them, maybe just a tad under. So I'm going to say this is 36. And we'll say 36.4, not quite halfway between 36 and 37. Now, because this last digit is estimated, when you would have read your graduated cylinder, you might have said, yeah, it looked like halfway between, and you would have come up with 36.5. It doesn't matter. we better both have that 36, but that estimated digit, we might estimate that differently from each other, but we still have to put it in. That's part of our measurement. It tells us about how precise our measurement is. All right. Well, how many sig figs do we have here? 1, 2, 3. So we have 3 sig figs in this measurement. And finally, one more example here. We're looking at this graduated cylinder. Actually, this is a burette because the numbers are going down as you go down. So we have 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 tick marks between that 20 and the 21. So that must mean each tick mark is 0.1 milliliters. So where are we on our scale here? We're at 20, 21, 20.1, 20.2, 20.3, not quite to 20.4. So I look at that. Is it closer to the 20.4 or the 20.3? It's closer to the 20.4, and it's really close to that 20.4. So I'm going to estimate this measurement to be 20.39. I estimate that last digit there, that 9. Again, reading off of our tool, we all should get the 20.1, 20.2, 20.3. We all should start with that 20.3. But that last digit we might be in disagreement with. And that's okay. That's all the more accurate our tool is to the 10th of a milliliter. How many significant figures do we have here? 1, 2, 3, 4. All right, so that's just a quick review of how we read our measuring instruments and how we figure out what our number of significant figures are. So now just a couple quick more notes to wrap this up. When reading someone else's measurement, how do you know which numbers are significant? How do you know which numbers are significant? Well, to answer that question, our significant figures are the numbers that were actually measured or estimated. So if we look at the page back where I was telling you how to read those tools, we wrote down the numbers that were measured, and we always added one more digit at the end, our estimated digit. So significant figures are these numbers that are actually measured or estimated, not just placeholders. So you might ask what a placeholder is. That's what we're going to talk about next. To understand a placeholder, we need to understand what happens if a number is a 0 or a number is not a 0. All right. Non-zero numbers, so anything other than a 0, any digit other than a 0, are always going to be significant. They're important in our measurement. They help us understand the precision. Zeros, on the other hand, it depends. Unfortunately, it depends, right? If the 0 is in between some non-zero numbers, that 0 is significant, right? Zeros can also be significant if they don't need to be there as placeholders. In other words, and I'll explain that here in a second. In other words, they're measured digits. They're measured or that last estimated digit. Zeros are also significant when there's a bar over them. Some of you might have seen this in your math class. That bar represents that digit repeating. All right, so let's go, and I'll explain placeholders here a little bit more in these examples I'm going to show you. So now, in the last few bits, I want to draw a box around the significant figures in each of the following measurements. Now, so really what this is going to be, we know all our non-zero digits are always significant. So if we see a non-zero number at the beginning and a non-zero number at the end, we know all the numbers in between are significant, right? So on this one, if I can get it to work here, 7.003. Those zeros are in between, right? So that meets our first criteria for our zeros are significant when they're in between non-zero numbers. So 7,003, all 7.003, all 4 digits are significant. Let's look at the next one. If we look at the next one, we got those zeros are in the front. These are what we talk about as being placeholder digits. We needed to put these zeros here so we could show what place that 3 and the 4 go in our answer. And this is a little hard for me to click on here. Let's try this a slightly different way. There we go. 0.34. So those leading zeros, those are zeros. They're not in between other non-zero numbers, so they're not significant. And they are indeed placeholders, right? We didn't measure that 0.00. That wasn't on our measuring tool, but we had to put those there so we had a decimal point in the right place. Let's look at our next one, 75,000. What about these? Did we measure all those? Well, if we would have measured them, we would have needed to put a decimal point over here at the end to indicate that we did measure all those zeros. Without the decimal point, there are only placeholders. They're to move that 7.5 over to the correct place in our number. So here, only the 7 and the 5 are significant. 18.00. Now, when we look at this one, I want you to be careful about it. We didn't put 18.00000. We didn't have a bunch of repeating zeros there. But we did have some, and they're on the right side of our decimal. Right? So there's a non-zero number, then there's our decimal, and we have some zeros. These zeros are going to be significant. They're not simply placeholders. We didn't need to put those zeros in here to make sure that our decimal point was lined up in the right place. Right? Anytime you have to put a 0 to make sure your decimal point lines up, that's a placeholder. Right? So like here in 0.0034, we added those zeros to make our decimal line up. Here in the 75,000, we added the zeros here to make our decimal point line up. We didn't need the zeros here to make our decimal point line up in our 18.00. So all those are significant. I think those are the harder ones to get through. 50.9, non-zero numbers are always significant. 50.9. Here we have 0.892. Now again, that leading zero here, that beginning, that's a placeholder. That's to help us line up our decimal. So it is not significant. We have the 892. We have 3 significant figures here. So look at our bottom row, 9.30. Again, this 0 here at the end, it wasn't needed to get our decimal point in the right place. So this is not a placeholder. All these digits are significant. 9.30. 902.5. There's a non-zero at the beginning, non-zero at the end. All 4 of those digits are significant. Now 7,300. Here we have a bar over them, like our third criteria here, and our zeros are significant. So all of these zeros are significant. If I can get this to line up, all those zeros are significant. Right? Now, similarly here with our 80,000, it's a little bit harder to tell where our zeros are that are making our placeholders. That's what our bar is telling us, that we actually read that 0. It's like over here in the 7,300. That bar tells you read the 0. So what are our significant figures here? It's the 8 and the 0. The 8 and the 0. Right? Those two are our significant figures. Okay. 200 meters over here, no bar. That means only the 2 is significant. 40.0. Now again, this last 0 over here, we needed that so we could line up our decimal point. This is not a placeholder. All of these are significant. Now, I've given you guys a worksheet. Please practice a little bit on that worksheet to make sure you have remembered how to use your significant figures correctly, and we'll go over that more on Wednesday. All right, the second part of what I wanted to talk today was how do we do our calculations with our variables? How do we do our calculations with our measurements when there's a power involved? So like squaring, if we square something, right, that's something to the second power. Or if we cube something, that's something to the third power. What do we do? How do we make those calculations, those conversions, as we go from inches to square inches to square feet, for example? And then finally, I'm also going to talk about rates. And we'll talk about miles per hour, meters per hour to meters per second or something like that. So we had 2 different units in that measurement, and usually for a rate, and usually that bottom measurement is a unit of time. So let's get through and talk about our powers, our rates, our powers rather. So how do we do that? If we want to know how many inches make a square foot, well, we know we're starting with 1 square foot, and we're asking how many square inches are there in 1 square foot. So let's start off. What are we asked? We're given 1 foot squared. That's the way to write square foot. Put a little 2 in your exponent. And this is equal to how many square inches? Again, that 2 is an exponent. So let's go through and write our equation. We're started with 1 square foot. We know we're going to inches. So how many inches in feet? We got to find that relationship. Well, we know there are 12 inches in a foot. 12 inches in a foot, right? So which one goes on top in our conversion factor? Well, really a better way to say it is which one goes on bottom. But the one that goes on the bottom is the one we started with. We started with foot. So when we write our conversion factor here, we're going to say 12 inches over that 1 foot. Again, that foot has to be in the bottom because it started off in the top. Now it's squared, right? So that means we have 2 of these. We have to have another power, another factor. We have to do that 12 inches divided by 1 foot again, right? Why do we need these 2 terms? Because we have a 2 here. We have foot squared. So we have to have that conversion factor between inches and feet in there twice. All right. So now let's go through. How to make sure we've set this up right. We didn't set something up backwards. Well, we want to make sure that our answer is just inches squared. So let's cancel out our units as we go through. Here we have a foot in the top. We have a foot in the bottom. We have another foot in the top. We have another foot in the bottom. Right? So we've crossed out all of our feet. What are we left with? An inch in the top and another inch in the top. Inch times an inch. Those are square inches. So our answer is going to be, we have to multiply our numbers together. 1 times 12 times 12 gives you 144. What are our units? Inches times inches, inches squared. All right, let's do one that's a little bit harder because it's cubed or cubic. And we can go with a similar kind of logic. How many cubic inches do you need to make a cubic foot? So our question is we write this as 1 foot cubed. Again, that 3 is an exponent. And we're asking how many cubic inches are there? So we're going to start it the same way. We're going to start off with what are we given? We're given our 1 cubic foot. We know we're going to inches. So we know our next variable, our next term, our next factor is going to involve feet, and it's going to involve inches. So we have to write that as a ratio. It's 12 inches in a foot. Which one goes on top? Does the foot go on top or do the inches go on top? Well, since we started with feet, we're going to put that feet in the bottom. Right? And we put our 12 inches in the top. Now, because this is cubed or has a power of 3, we have to put this factor in here 3 times. So we're going to put another foot on the bottom with the 12 inches on the top and another foot on the bottom with 12 inches on the top. So we've done all of our terms here. So let's go through and make sure we didn't make a mistake. So we're going to look through. We got feet on the top here. We got 1 power foot here. There's 1 power foot on the bottom. We got another power foot on the top. There's a foot on the bottom. And finally, we have a third power of feet in the top in that first term. There's another foot in the bottom. So we've canceled out all our feet. Right? What's left? Inch times inch times inch. That's inches cubed. Awesome. That's what we're looking for. So we're going to punch this into your calculator, 12 times 12 times 12, and you're going to come up with 1,728. And again, we get our units inches cubed because we have inches times inches times inches. So you can always do, if you do your math right, if you set up your terms right, you're going to start with the units you were given, foot cubed. We put in our conversion factors. What's left after we cancel all of our units out? Inch times inch times inch, inches cubed. That's what we were looking for, how many inches cubed we have. So that's how we're going to do powers. And all it is look at that power. That tells you how many times you have to have that conversion factor in there. Let's talk about rates now. Let's do one more set of powers, and then we'll talk about rates. So here, let's try 200 cubic feet to cubic yards. We're going to start off with our 200 cubic feet. Right? We know we're going from feet to yards. So we're going to have to put our next term here is going to have yards and feet in it. Well, what's our conversion between yards and feet? It's 1 yard is equal to 3 feet. Right? So which one goes in the bottom? We started off with feet, so we better put our 3 feet in the bottom. And there's our conversion factor from converting from yards to feet. But we have feet 3 times here. Feet is cubed. So we're going to need a conversion factor 3 times. All right. Let's go through and make sure we're going to cross out everything that we can. Make sure our units work out right. We've got feet cubed. Well, there's a foot in the top. Here's a foot. Here's a foot in the bottom. We have another foot in the top. Here's a foot in the bottom. And finally, we have a third foot in the top, and there's our third foot in the bottom. Right? So all of our feet have canceled out here. We're left with yard times yard times yard. We're left with cubic yards. That's exactly what we were looking for. So we're going to punch into our calculator. Now, what I want you to do is I want you to multiply all the numerators together and all the denominators together. So you're going to have 3 times 3 times 3 is your denominator. You have 200 times 1 times 1 times 1 is your numerator. So I want you to punch into your calculator 200 divided by 9. Right? I only want you to do that division 1 time. Figure out what your numerators are. figure out what your denominators are, then do your division. Don't be sitting there going 200 divided by 3, divided by 3, divided by 3. You're going to make a mistake. It's too easy to make a mistake. Multiply all your numerators together, multiply all your denominators together, and do that division only at the end. All right? If you punch that into your calculator, come up with 7.41 cubic yards. And finally, let's do one more. We're going to start with 5 square meters. We're going to square kilometers. So again, what are we starting with? Square meters, 5 square meters. We know we're going to kilometers. So what's the conversion we know between kilometers and meters? We know that 1 kilometer is 1,000 meters. Well, which of those terms goes on the bottom, the 1 kilometer or the 1,000 meters? We start with meters here, so we better put our meters in the bottom so we can get it to cancel out. All right, so there's one of them, but we're having meters squared, so we better do it another time. There's our 1,000 meters. All right, and we're going to come back. So 5 meters squared. Let's go through and we'll show out where did we cross out our units. Make sure we got our units crossed out right. We got meters here in the top. We got a meter here in the bottom. We got another meter here in the top. We have another meter here in the bottom. So now we've got 5. So our units canceled out. We're left with square kilometers times kilometers. Square kilometers. That's what the question asks us for. Let's do our math. 1,000 times 1,000. What does that give you? That gives you 1,000,000. It gives you 1,000,000. So we're going to take 5 divided by 1,000,000, and that's going to give you, depending on how your calculator is set up, it might put 0.000005. Or it might just tell you 5 times 10 to the negative 6. Whichever your calculator puts out, that's right, just as long as you know what that means, right? Or you can write the numbers down correctly. And then we know our units are, whoop, I have meters squared. These units are really kilometers squared. Let me put the kilometers back in there. Okay. So there is our answer to that one. Again, we figure out what our conversion is, kilometers and meters. How do I know which one goes in the bottom? We started with meters. Meter goes on the bottom. Double check our work by canceling out our units. We have meters on the top twice. We have meters on the bottom twice. We're good. We're left with just kilometers in the top twice, which is what we're looking for, square kilometers. All right, and the last little bit for today, I want you to go through here. We're going to do some conversions involving rates. And so our rate usually is some sort of unit per unit time, something per unit time. Right? It's usually, it could be a distance, it could be a mass, it could be a volume. There's all sorts of things we could be talking about. But usually when we're talking about a rate, the bottom unit is a unit of time. So let's go through and do this. 55 miles per hour to meters per second. I hate that we do this. This is an English abbreviation, but usually when we put the meters, M by itself, it usually means meters, unless it's in a MPH, which is miles. I hate that, guy. Sorry, that's just the way the English language has worked itself out. So how do we write 55 miles per hour? Well, that per tells you that the hour is going to have to go in the bottom. So we started off. What's our number here? We're starting off with 55 miles, and we got to put it over 1 hour. 55 miles per hour. Well, notice we have 2 units here. We're going to have to convert both of those units to what our ending units are. So we have to convert the miles here to meters. And we also have to convert the hour here to seconds. So we're going to do that in 2 steps, a couple steps. The first thing to do, let's take our miles and let's convert it into meters. Well, if you remember from the beginning of our notes last week, we said that 1 mile is approximately 1.6 kilometers. 1.6 kilometers, 1,600 meters. So we're going to use that for our conversion, 1 mile and 1,600 meters. Which one goes in the bottom? We started with miles. Miles go in the bottom. So we put our meters on the top. 1,600 meters per mile. This is nice. Do we have to go any farther? Well, we've got our miles on the top. We've deleted our miles from the bottom. So we got rid of our miles. We're left with meters. That's what we're looking for. We want meters on the top. Let's take care of our time. Right? We started with hours. We know we're going to seconds. So we have to put in a factor here to go from hours to seconds. Well, unless you happen to know that off the top of your head, I don't remember that. But I know how to go from hours to minutes and then minutes to seconds. So let's take our hours and convert them into minutes. 1 hour is 60 minutes. What number goes where? Well, hours is in the bottom over here. So it better go on the top over here so we cancel out our hours. That means our 60 minutes will go in the bottom. All right. But we weren't asked for minutes in our answer. We were asked to get it to seconds. So we need to go another term. We need to convert that minutes to seconds. Again, we know 1 minute is 60 seconds. How do we know which one goes on top, which one goes on the bottom? Minutes is in the bottom here, so it better go on the top in our next term. We put our 60 seconds in the bottom. So let's look at our time units. We started with hours. We canceled it out by having it in the top. We have minutes in the bottom. We canceled it out by having minutes in the top. So what are we left with? The only units we're left with is meters on the top, seconds on the bottom. That's exactly what we're looking for. We know we've got our problem set up correctly because our units balance and make sense. Let's put that into our calculator. 55 times 1600. We're going to multiply that out. We're going to multiply the 60 times 60. And we're going to divide those two results by each other. So 55 times 1600. Then we're going to divide it by 3600, our answer. And you'll come up with 24 meters per second. All right, guys, one more example for the day and we're done. 83 meters per minute to centimeters per second. So how do we write that? We write 83 meters on the top. We put 1 minute on the bottom. That's what it told us, meters per minute. Now we know we're going to centimeters. So we know we have to have a conversion between meters and centimeters. We know it's 100 centimeters to every meter. Which one goes on the bottom? Meters is in the top here. Meters better go on the bottom here. So that's how we're going to write that conversion factor. And that's all the farther we had to go for our units of distance, right? We got our meters canceled out. We're just left with centimeters. That's what our answer wanted, centimeters. All right, and finally, let's look at our time. We have minutes here. We want to go to seconds. So we know we got 1 minute and 60 seconds. Minutes in the bottom, so we better have minutes on the top here so it can cancel out. We have 1 minute divided by 60 seconds. What is that? Let's punch that into our calculator, 83 times 100. Then we divide that number by 60, and you're going to end up with 138 centimeters per second. Well, hopefully this was all just a quick review for you guys. This will be handy when we go through the rest of the year in physics, knowing how to do your multiplications when we go from powers, right, square meters to square kilometers, or we're doing rates, miles per hour to meters per second. Just a quick review so you know how to do those. All right, guys, thanks. There's a problem set for you to do. Take a look at those. And we'll talk about that on Wednesday as well. Take care. All right, now everybody that we have done the video lecture for today, please don't forget to do that lecture notes quiz at the bottom of today's folder. Make sure you click submit when you are finished with the quiz. Thanks.